there's probably a malignancy somewhere. You just don't see these things in great numbers at any time, really. And you see that basophils are so loaded with granules, it's hard to even see the nucleus on that thing. Okay? Agranulocytes. Two different cell lines will be lymphocytes and monocytes. We'll start with the lymphocytes. There are a whole bunch of different types of lymphocytes. We're going to focus on only a few of them. First, you have B and T lymphocytes. There's another lymphocyte category called null cells. B and T lymphocytes are characterized not histologically. When you see them on a slide, you can't tell which one's which. It's the surface markers that distinguish B from T. Also, their function is different. But there are some cells that don't have the markers for B or T. They're called null cells, or neither. Well, they're called neither because they're really embryonic T cells. About 80% of the lymphocytes in circulation are of the T variety. 20% or so are of the B. Of the T cells, there are a bunch of different types, but we're going to focus on two. Ones that have cell surface markers that are positive for CD8, which is a cell surface protein, and others that are positive for a marker called CD4. They're two separate markers. They're not together on the same cell. You either have the CD8 positive T cell or a CD4 positive T cell. CD4 cells are also called the helper cells. CD8 are called killer cells or NK cells, natural killer cells. These are obviously part of the immune system, and your immune system works by recognizing self versus non-self. We're going to talk about cell surface markers called the MHCs, the major histocompatibility complex. You might also know it as HLA, human leukocyte antigen markers. HLA is the same thing as an MHC. All right. This is what a lymphocyte looks like. You don't see the nice granules in there. That's why it's part of the agranulocyte. As I said, histologically, you can't distinguish if that's a T or a B. So let's talk about HLA. There are certain cell surface markers that predispose to disease. It's not necessarily the cause of the disease. It could be the cause of the disease, but it's not necessarily, because everyone with that particular HLA type doesn't get the disease. And not everybody with the disease has that type. So it's a trend towards the disease without being causation. For example, HLA-B27, most people with that particular major histocompatibility complex are going to be men in their 20s with ankylosing spondylitis. And when you get into things like diabetes, type 1 diabetes, because that's an autoimmune disease, not type 2, type 1. Sjogren's disease, these types of things, they have trends that if you have these types of HLA markers, it's consistent with the disease. All right, I'm just throwing that out. You can envision that, wait a minute, if these are autoimmune diseases and these are your cell surface markers. What is autoimmune disease? You are attacking yourself. Is that not what's going on here? Is that why there is a relationship between these and these diseases? There probably is, it just hasn't been equivocally determined yet. All right, so let's switch gears and talk about MHCs for a minute. There are two types, there are two classes. Class 1 MHC that are on every cell of your body except B cells, B lymphocytes. B lymphocytes have class 2 MHCs. So class 1s are everywhere, class 2 are on B cells. Now, this illustration here, I'm going to expand on this because what this illustration here is showing is they describe here it's on the cell surface by class 2 MHC. Where are class 2 MHCs? On B cells. So this illustration is showing you what happens with B cells. However, this happens with every cell in your body, which would be class 1 MHCs. This is how you get recognition of you. So as you're a little bitty embryo, you have apoptosis, you have cell death, you have all these pieces of protein fragments and amino acids circulating in your body, right? Peptides and all sorts of these little fragments. These little pieces and parts of you wind up as, you can consider them as antigen molecules. Antigen molecules. But they're you. It's you, right? And these antigen molecules are going to be like 3 or 4 or 5 amino acid sequences long. They're little tiny fragments of you from your own cellular destruction. They get internalized like this. They're broken down into pieces and parts, and then you make MHCs, package them in these granules. You mix them with these little pieces of you, and you return them to the surface as you. That's how you recognize you. Because what is on here are pieces of you. If I take my kidney that has pieces of me and put it in you, I have different expressions. That's why we're different. And it's this is what the immune system is looking for. I'm looking for MHCs that aren't expressing me. If I find them, I'm going to attack them. Everybody follow me? All right. It's simple. It's simple. So if you look at the thing here, here's the antigen presenting cell. Let's say that's my cell that's in you now. There's the antigen fragment of Dan right there. There's my MHC, class 1 or class 2. Doesn't matter for purposes of this discussion. But here's Mr. T cell comes along. T cell has a receptor on it that's looking for that antigen MHC complex. It's going to bind to it if it recognizes it. And then it's going to solidify that binding with either a CD4 or a CD8 cell surface protein. It says CD4 or CD8. You don't have both. Remember I said you don't have both. And that produces this complex here. Now you've got your T cell bound up to my donated liver cell, kidney cells. We're fixing to have rejection. Before we do, let's go into this. This is called clonal deletion. Back when you were a little bitty embryo, you had these embryonic T cells. Those embryonic T cells display the T cell receptor and both CD4 and CD8 receptors. They get from the bone marrow into the thymus, where you've got these thymic cells here, where the embryonic T cell is presented to them. What you don't want is that embryonic T cell binding to a thymic cell, because that's your thymus cell. You don't want to release out into the circulation something that's going to recognize you. If it does recognize you, if you get binding here and here, you got to get rid of it. You got to delete it. If it recognizes you, you have to delete it. If it doesn't recognize you, we can let it enter the circulation. And as that T cell enters the circulation, it will lose either the CD4 or the CD8 and become one or the other. That's what you want in circulation. How does autoimmune disease work? Pernicious anemia, rheumatoid arthritis, diabetes type 1, Hashimoto's thyroiditis, Graves' disease. I could go on and on and on and on. How do they all work? You let that son of a bitch into the circulation. You let the cell that recognized you into the circulation. You destroyed your beta cells. You destroyed your thyroid cells. You destroyed the parietal cells of your intestine, of your stomach. They attacked them. You attacked the lining of your synovium. You gave yourself RA. Not OA. Osteoarthritis is just wear and tear. Rheumatoid arthritis. That's how it works. Pretty simple, huh?
So simple.
Yeah. Okay, so here's a summary. Everything's summarized here. Now, okay, so when you get binding, let's say, what is the purpose of this CD4 and CD8? Well, here we go. CD4, they bind to class 2 MHCs. CD4 only binds to class 2 MHCs, so they only bind to B lymphocytes. CD4 T lymphocytes only bind to B lymphocytes. Class 2 expressing non-self. Right? Expressing non-self. That B lymphocyte has been activated. It's been exposed to some bacterial proteins or some proteins from somebody else. These two cells, the CD4 plus cell, T cell binds to the B cell, causes that B cell to pump out immunoglobulin. This is humoral immunity. It produces antibody to the antigen that was on the T cell receptor. You follow that?
No.
So why does this binding occur? The binding occurs because it recognized non-self, like a bacterial protein, or viral protein, or fungal protein, or a protein from a transplant that's non-self. That class 2 MHC expressing non-self bound to the CD4 plus T lymphocyte and caused that B cell to to produce antibodies to what's on the surface. In AIDS, not HIV, in AIDS, what is the diagnosis of AIDS? When does HIV become AIDS? When the CD4 count drops below 200. It has nothing to do with viral load. It has nothing to do with anything else. It has to do only with the CD4 count dropping below 200 cells per milliliter. If you don't have enough CD4 cells, you can't mount an immune reaction. That's why they have opportunistic infections. Kaposi sarcoma is an opportunistic infection. What did I say caused Kaposi sarcoma the other day? It's a virus. Kaposi sarcoma is a tumor caused by a virus. Why does that happen? Because you don't have the CD4 cells to fight it. Why do you get PCP pneumonia, or it's called Hematopoiesis now? You can't make the antibodies. You don't have the B cell activation to mount the immune response. You follow me? Kind of makes sense, doesn't it? I mean, if you know, it's going to take a while sitting at the dining room table and follow these. Yeah, I'll admit that. It takes a minute to figure this out. But it's rather simple once you get down to it. Okay? How about CD8 cells? These little dudes, these are nasty. These guys are going to bind to class 1 MHCs, which are on every cell type of your body except the B cells. And when they bind to this renal cell that's expressing not you, what the cell does is injects a toilet paper type ring of proteins into the cell membrane called perforin. It punches holes in the cell membrane of whatever cell it's attached to and causes the cell to spill its guts, leak out, or whatever you want to call it. You see what I mean? It punches holes in it. It kills it. This is cell-mediated immunity. This is what happens with rejections. Graft rejections. Graft versus host disease. This is it. Right here. I'm not sure that it says that, but that's what it does. Okay? Follow me? Easy. That's it. That's it. Okay? All right. Development of lymphocytes, really easy. Lymphoblast, prolymphocyte, and lymphocytes. Lymphoblast are what you're going to see in ALL and CML. Monocytes. Monocytes are kind of cool because they're not as it says here, a mature cell in circulation. They stay in circulation just a few hours, and then they crawl out into the connective tissues where they mature into a macrophage. Tissue macrophage. They just scour the tissues looking for stuff to eat. They live a while and they die. That's just cool. Okay? The more places where you have more likely things to get through, the more monocytes and macrophages you'll see, like around your oral cavity, your anus, your ears, your nose, that type of thing, where you have openings to the outside. Okay. Here's the thing that looks like the little Pac-Man. You see it? It kind of looks like the Pac-Man. It does to me. I don't know. Yeah, there's a platelet up there, and so, okay. Plasma cells are interesting. You know when I'm talking about the class 2 MHC T cell, it attaches to a B cell and activates it, so it turns out, it starts churning out immunoglobulin. The cell that churns out the immunoglobulin is a plasma cell. A plasma cell is a mature or activated B cell. And it is a monstrous IgE secreting factory. IgEs, when they're released by the plasma cells, and plasma cells are interesting because they're very characteristic. When you see them in the tissues, they're not in circulation, they're in the tissues. Some people say that the basophil and the plasma cell are the mast cell. Mast cell is next. Are sort of the same cell. They're not really the same cell. They don't even come from the same cell line, but they have a similar function. Anyway, I'm not sure what oh, clock face. If you have the nucleus, the chromatin in euchromatin is arranged like that, so it looks like the face of a clock, the numbers on a clock. Plasma cells are very characteristic in histology slides. And those too are abundant where you have openings to the environment. Plasma cells. The IgEs bind to mast cells that secrete all sorts of good stuff. Slow reaction substance of anaphylaxis, also histamine and heparin. And this is the characteristic schematic here. I don't know if you can see, you really can't see the clock face. Yeah, kind of right there. You know, if you squint your eyes and imagine, go to Colorado and come back with a positive urine test, you could probably say that's a clock face. Anyway, how about that dumbass lady who is the advocate for pot? Came to Oklahoma to give a speech with a car loaded with pounds of pot. How stupid can you be? I learned a new word this weekend. It was in the Daily Oklahoman. You know that a person who works in one of those pot stores is called a bud tender? It was in the Daily Oklahoman. I didn't know that. There was a picture of a guy, a bud tender. I'm glad I was able to teach you guys something. Here's the plasma cell, here's the IgEs, there's the mast cell. So now you've got these sensitized mast cell. Whenever you get an antigen presenting to the mast cell, it will degranulate. It will degranulate, dumping out the heparin, histamine, the eosinophilic chemotactic factor, a slow release of substance anaphylaxis, and you get bad stuff, allergic reaction. There is a medicine to treat asthma that is called a mast cell stabilizer, and that's how it works. Yeah, it prevents the mast cells from degranulating. Yes, Professor Rourke.
Which mechanism, how do you get transfusion reaction? Is it like transfusion reaction?
How does what? Yeah.
Is it CD4?
A transfusion reaction. It would have to be a CD4 related, because it'd have to be immunoglobulin, not. No, if the transfusion reaction is immediate, like an anaphylactic reaction, versus occurring the next day, the next day may be more of a CD8 issue. But yeah, so, okay. Oh, was that it?
Yeah.
I was just getting wound up. Oh, we still have time. Let's go.